This is stochastic process, module 5 continuous time Markov chain, and this is a 7th lecture, communication systems. In the last 6 lectures we have discussed the continuous time Markov chain, and in the last 2 lectures we have discussed the application of a continuous time Markov chain in queuing modeling. In this lecture I am going to discuss the application of continuous time Markov chain in communication systems. So, this talk divided into 3 parts. The first I am going to discuss the application of CTMC in 2G cellular network system, and then I am going to discuss the 3G cellular network system. 2G means a second generation and 3G means a third generation cellular network system. And finally, I am going to discuss the simulation of queuing systems. That is basically a discrete event simulation. The cellular system or wireless system is nothing but a network system in which the calls are generated and calls are occupied for some time and leave the system. And this consists of many cells. Each cell is of the hexagonal shape, and our interest is to study the performance analysis of cellular networks using continuous time Markov chain. This is the center cell, and all other 6 cells are called the neighbor cells. Either we can make the performance modeling for the whole cellular networks, or we can make the model for only one cell first, then we can apply the hierarchical modeling for the whole cellular networks. So, in this I am going to discuss the performance analysis of one cell in a cellular networks. Cellular networks or wireless networks, our interest is to study the performance analysis. Suppose you think of a bandwidth as the channels. Whenever some calls originated, it uses the one cell for the one channel for the communication. Suppose you assume that we have a finite number of bandwidth or a finite number of channels in one cell. Suppose that you make it as some capital N finite quantity. So, whenever the calls originated, then it will take one channel from the cell, and the call will be for random amount of time, it will be keep going, and once the call is completed, then the channel will be released. We have designed calls with the 2 types of calls. One is called the handoff call, the other one is called the new call. Handoff call is nothing but a call in progress handed over to another cell due to user mobility. In that case, the channel in old base station, that is in the previous cell, is released and ideal channel given to the new base station. So, that is the way the handoff phenomena operates. Therefore, I consider the call into 2 types of call. One is called the handoff call, the other one is a new call. Handoff call is nothing but the call originated from the neighbor cells and coming into the cell where we are studying. That means, suppose the calls are originated in these neighbor cells and coming into the underlying cell which we are considering, then that calls are called the handoff calls. So, either it can come from this cell to this cell, or it can come from this cell to this cell, and so on. So, therefore, the calls originated from the neighbor cells and coming into the underlying cell, that is called the handoff calls. Whereas the calls originated within the cell itself, that call is called the new calls. That means the channel will be channel will be given from the same base station of the cell, and once the call is get over, then the channel will be released. Therefore, the calls originated from the neighbor cell is called handoff calls. The calls originated within the cells are called the new calls. These are all the two types of calls coming into the system. If there is a bandwidth or channel, then the calls will be allotted, and after the calls are completed, the channel will be released. So, there are two types of call completion also. Either the call is completed within the cell itself, not moving anywhere. Due to mobility, there is a possibility the calls can be originated within the cell or coming from the neighbor cell. It can last for a whole time in the cell, and it would have moved to the other cell also. In that case, it is called the handoff to neighbor cells. The way the calls are originated from the neighbor cell coming into the cell, the same way you can discuss the outgoing also. The calls can be completed within the cell itself, or it's keep going to the neighbor cells. That is called the handoff out calls. Now I am going to discuss what is the concept of dropping and blocking probability. Since the handoff calls are having the higher priority, because the calls are already originated and keep coming into the cell, and there is a possibility it can move into the other cell also. Therefore, we should give a higher priority to the handoff calls. There are many ways of giving the higher priority to the handoff calls. The one easy way is reserve few channels for the handoff calls. That means out of capital N channels, you reserve few channels for the handoff calls, not physically few channels. Whenever you have left out a few channels in the system, in the pool, then if that number is more than the reservation, then you keep allowing the new calls as well as handoff calls. If you reserve some number of channels for the handoff calls, and the available bandwidth or available channels at a time of arrival, it is less than that, then do not allow the new calls. So, only the handoff calls will be allowed whenever the number of available channels are going less than or equal to the prescribed number. So, that is called a fixed reservation channel policy. So, suppose out of capital N channels, you reserve some G channels for the handoff calls. That means if a number of ideal channels less than or equal to G, then the new call will be blocked. Whereas at the time, if the handoff calls enter into the system, then it will be channel will be allocated. If no ideal channel is available, that means all the channels are busy with calls, then handoff calls will be dropped. Obviously, new calls also will be dropped if no channel is available, but if the number of ideal channel is less than or equal to G itself, from that point onwards, the new calls will be blocked. So, our interest is to find the blocking probability and the dropping probability. So, the dropping probability is nothing but the handoff calls are dropped because of no ideal channel in the system. The blocking probability is nothing but the probability that the new calls are blocked because the number of ideal channels are less than or equal to G. Once we are able to find out these two performance measures, then using that one can design better cells, how to for a given number of channels, how we can reduce the blocking probability as well as the dropping probability. So, these measures we are going to find out using a continuous time Markov chain. So, for that we are going to make the few assumptions, so that the underlying stochastic process will be a continuous time Markov chain. And here we are making a model for only the one cell, not the whole cellular networks. So, we make the assumption the calls are in a Poisson process for the new calls as well as the handoff calls, and both are independent. We make the rate lambda 1 is the arrival rate for the new calls and the lambda 2 is the arrival rate for the handoff calls, and both are independent. Therefore, the call arrivals, either it is a new call or handoff calls, that will be a sum of two Poisson. Therefore, that is also Poisson process with a parameter lambda 1 plus lambda 2. And also we make assumptions over the call completion, either the call completed within the cell, that is exponentially distributed, the time for the call completion within the cell, that is exponentially distributed with the parameter mu, as well as the calls handoff to other cells, that is also exponentially distributed with the parameter lambda 2, so mu h. And we make the assumptions the call completion as well as the handoff to other cells, that is also independent. And we have a total number of n channels is capital N. Out of that, we reserved G channels for the handoff calls, and these channels are called the God channels. So, with this assumption, that means we are considering only one cell, and the new calls from that stream is a Poisson stream, and this stream is also Poisson stream, and the call duration, either call completion is exponential distribution or handoff to the neighbor cells, that is also exponential distribution, and we have total number of n channels. Out of that, G is for the reserve channel, and accordingly the Markov chain, first we are going to make a stochastic process. Stochastic process is a CT, that is nothing but the number of busy channels, or each channel is allocated for one call. Therefore, at time t, what is the number of calls, that is the stochastic process, that is a random variable. So, over the t, that is a stochastic process, and since it is a number of busy channels, therefore, it is a discrete state continuous time stochastic process. With the assumptions we have discussed in this slide, the stochastic process will be a continuous time Markov chain. Only nearest neighbor transitions are allowed. Therefore, this is not only a continuous time Markov chain, it is a special case of continuous time Markov chain, that is a birth death process also. So, it is a variation of MMCC queuing model with the rates are different. That means the birth rates are lambda n minus g, after that the birth rates are lambda 2. If you recall, this lambda is nothing but lambda 1 is the arrival rate for the new calls, and lambda 2 is the arrival rate for the handoff calls, and lambda here it is lambda plus lambda 2. That means whenever the number of busy channels, it is starting from 0 to n minus g minus 1, both new calls as well as handoff calls are allowed into the system. Therefore, the arrival rate is lambda, birth rates are lambda, whereas the number of busy channels from n minus g to n minus 1, the birth rates are only lambda 2, because the new calls are blocked. Only handoff calls are allowed whenever the system size is n minus g to n minus 1. Whenever the number of busy channels is 1, 2 and so on till n, either the call is completed or the calls are handoff to the neighbor cell, and both are exponentially distributed with the parameters mu h respectively, and both are independent. Therefore, the rates are going to be mu 1, mu 2 and so on, where mu 1 is equal to 1 times mu h plus mu n, and mu t is nothing but 2 times mu h plus mu n and so on. So, this is the death rates. Therefore, the number of busy channels at any time, that is a birth death process with the birth rates lambda till n minus g minus 1, after that it is lambda 2, and the death rates are n times mu where mu is nothing but mu h plus mu. Either I can use this notation or the other notation.